Hello everyone. I want to hope that you're all doing fine and I'm excited about today's experiment. Have you ever wondered why we use salt to melt ice on sidewalks during winter, even though we know that the salt doesn't warm the sidewalk? Well, hopefully, by the end of this lab experience, you will be able to chemically explain what is going on when we add salt to ice to melt it. Okay, so this lab is entitled Molar Mass Determination by Freezing Point Depression. So basically we are going to use the concept of freezing point depression to determine the molar mass. We know that molar mass is an important quantity in chemistry, and it is basically the foundation of most calculations that we do. And there are various ways to determine molar mass. And so today we'll use this concept. And for that to happen, we need to understand that when solutes are added to liquids, they have some influence on some of their properties. So the property we're going to talk about today is the freezing point. And when comparing when looking at this concept, we have to first of all know the freezing point of the pure solvent and then compare its freezing point when a solute has been added. So they say we'll then use this information to calculate the molar mass of the substance or the unknown substance that we are going to add to our known solvent. Okay, so as I mentioned before, there are properties of liquids that are going to be affected by the number of solutes that are in the solution and not necessarily by the identity of that solute. So if as long as we have a specific number of molecules or moles in of the solute, then we can say that the higher the number, like we expect that this freezing point will be decreased by a certain amount, or the boiling point will be increased by a certain amount, or the osmotic pressure and the vapor pressure would be changed by a different amount. So we're not going to go deep into these other properties, but we'll focus more on the freezing point depression part. Okay, when when a certain number of molecules or amount of solutes are added into a pure solvent, then the freezing point of the solvent will be decreased by the amount given in this equation here, by the molar freezing point constant multiplied by molality of the solution formed. So freezing point is the temperature at which a liquid changes into solid. And so if, for example, we have a pure liquid that always melts at 40 degrees Celsius, but when we add a certain amount of solutes, then that freezing point would go down by a specific amount. Maybe that it would go down to 38 or 35 or whatever. But the change in temperature is basically the difference between the freezing point temperature of the pure solvent and the mixture of solvent and the solutes, the mixture of that solution. Then I is the number of ions that are formed. So for example, when you dissolve sodium chloride in a solvent, we are going to form sodium ions and chloride ions. And so because we have that one sodium ion and one chloride ion, our I becomes 2. But in today's experiment, we're using lauric acid, and in our solution, we'll assume that we do not have any number of ions being formed. So our I will be 1, and so our change in temperature would just be the molar freezing point constant that is characteristic for each solvent and multiplied by the molality. And molality is defined as the number of moles of solute divided by the amount of solvent in kilograms. So the units of solvent need to be in kilograms. Don't worry about this. We'll walk through an example just to show you how to get to the molecular mass starting at just the change in temperature and the molar freezing point constant. So let's walk through this example together. And I'm just going to insert this text box so that I have a place to write. Okay, just expand this and post this up here. So the question says a sample of pure T-butyl alcohol whose weight is 7.512 grams was found to have a freezing point of 24.7 degrees Celsius. When 0.662 grams of an unknown compound X was added to the alcohol, the mixture had a freezing point of 22.3 degrees Celsius. Calculate the molar mass of compound X. And then we are given the molar constant value here. The molar freezing point constant value as 12.8 degrees Celsius per molar for T-butyl alcohol. So let's start with writing our equation as it was from the previous slide. So change in temperature is equal to Kf. So I said that I will be 1, so we just don't need to write it in this equation. But our change in temperature is then we had 24.7 and now we have 22.3. So the difference between those two temperatures, pure T-butyl alcohol and then the mixture of T-butyl alcohol and our unknown compound, we now have a freezing point of 22.3 degrees Celsius. And this gives us a difference of 2.4 degrees Celsius. So going back to our equation, we have the value of our change in temperature. We also have the value of molar freezing point constant. And that means we are only missing molality value. And we can say 2.4 is equal to 12.8 times the molality value, which we are going to find. So to find molality value, you just take the 2.4 and divide it by the 12.8, which is your molar freezing point constant given for T-butyl alcohol. And your molality value will be 0.1875. All right, I hope you're with me this far. Now, how do we get from molality to molar mass? Because the question wants us to calculate the molar mass. We are only at molality, but we know the definition of molality to be moles of solute divided by kilograms of solvent. Do we have molality? Yes, we just calculated it. It's 0.1875. Do we have moles of solute? No, that's what we're looking for. Do we have mass of solvent in kilograms? Well, we have mass of our solvent, which is T-butyl alcohol, but it's in grams. So we basically just need to convert it to kilograms, and that would be 7.512 divided by 1,000, which should give us 0.007512. All right, so let's put in the values that we have and see what we get. So this should be equal to moles, sorry, that to be equal sign, moles of solute, and we are going to divide it by the amount of solvent in kilograms. It's 0.07512 kilograms. Okay, so because we are looking at moles of solute, then we will multiply, so we'll take this value since it's at the bottom and just cross multiply so that we have 1875 times 0.007512, and the moles that I have here is 0.001405. Okay, now we have most of our solute, which is compound X. We also have the mass of a non-compound compound X, because it's given here as we have 0.662 grams. So how do we get from these two to molecular mass? So we know that molecular mass will be mass of the substance divided by moles of that substance. And so we have 0.662 grams. I'll just write the units here. And then divided by the number of moles, which we calculated there at 0.001405 moles. And the final value that I have is 470.0035, which you can just say is 470. Let's say 470 grams per mole. All right, so we arrived at our desired molecular mass. So basically, when you go through our experiments, you will realize that you will go through the same calculation concept to get to your molecular mass. So just because you'll be given the amount of pure lauric acid, you will measure, or the experiment will determine the freezing point temperature of your pure lauric acid. It will give you the amount of a non-compound to add to your solvent. And then you will also obtain the freezing point temperature for the mixture. And then you have the molar freezing point constant for lauric acid, which is given to you. And you basically just follow the same steps to get to the molecular mass. And that is what we were talking about in the title of, this is how you determine the molecular mass from the freezing point depression of this pure lauric acid. So the experiment just entails melting your solvent and then cooling it and allowing it to change state from liquid to solid. So that constant temperature which the solvent changes from liquid to solid is your freezing point. And then you will do the same thing. You will have your pure lauric acid, and then a specific amount of a known substance will be added to your pure lauric acid, and you will melt them together and then allow it to cool and let it freeze, obtain that freezing point temperature, and then just use the difference to calculate the molecular mass of the unknown substance. So you will receive LogarPro files that look like this, where you see this red line is showing you the melting curve for pure lauric acid. The green one is showing you the melting curve for lauric acid plus your unknown substance. So the way you interpret this graph is just that this temperature is slanted here. This slanted line here is just showing you the decreasing temperature, but it's still a liquid. But when you see this constant line, it's telling you that the temperature is remaining constant for the liquid to change phase from liquid to solid. And so we expect that this should be the freezing point temperature. And so just look at what this line tells you and read the value of the horizontal line temperature, and that will be your initial temperature. Well, that will be your temperature for pure lauric acid, the freezing point temperature. And the same thing applies for your mixture where you have lauric acid and a non-substance. You see that the freezing point temperature goes down at, by some value. So just determine this constant line right here obtain the temperature for that, and then your change in temperature will be the difference between these two numbers. And with that, you should be able to plug it into the equation, determine the molality, and basically the moles of your substance and molecular weight. You will also have a list of identities for the different compounds. Once you have the molecular weight, you can compare it with the exact molecular mass um, that is given in the table. So this lab entails writing a formal lab report, and this should be expected to be a little bit longer and more in-depth. So please follow the style guide that shows you how to write a formal lab report, and make sure that you have everything in the guideline or all the information in the checklist so that you can get your your good grade in this. And if you need any help, make sure to contact your instructor for that. And this lab is due 2 weeks after your instructor assigns it to you. So just watch for that, and I wish you the best.